Hello, everyone, and welcome to the Warsaw B Meetup. Of course, this time not in Warsaw, but online. I'm Justyna, and I work at Polydia as People and Culture Lead, and Polydia is the organizer of this meetup. And first of all, I'd like to introduce our speakers, Riza and Alex. Thank you for being with us and for preparing your presentations. We are very excited to see them in a minute. After each presentation, the speakers will answer the questions. You can all use the Q&A and ask about anything, and the speakers will try to answer the questions. Also, after the presentations, everyone will get the questionnaire, the survey. So we would be very thankful if you'd answer those surveys to help us improve. It will just take a minute. It's, I believe, only 5 questions, and it's really, really valuable, and your feedback is very helpful for us. Of course, this event wouldn't be possible without our sponsors. So Google Cloud, thank you very much. And that's all from me. I wish you a great meetup and have fun. So Riza, it's your time.
My name is Reza Rokni, and I'm a data engineer, specifically in Google, working on Google Cloud Dataflow. So I've been at Google around 7-8 years, and for quite a few of those years, I have been working with Dataflow and Apache Beam within different roles. And what we're going to do today is just go through Tensorflow Extended as a machine learning pipeline framework, but from the context of Beam. So I've been working around building a pipeline for time series with some data scientists. I'm definitely not a data scientist, I'm a data engineer. And I'm trying to take some of those learnings on things that I've done that's got me quite excited about TFX and kind of create them back in this presentation. Again, thank you everyone for joining, by the way, and also in these really tough times. In preparing this presentation, I had to do it with my daughter screaming about not wanting to do homeschooling in the background. A great tip is to big headphones and high volume. I found that worked really well for getting things going. So the areas we'll go through today. So we'll do a high level of TFX, and this is from the data engineering Apache Beam side. For much more in-depth TensorFlow Extended, especially from the angle, one of my colleagues at Google, Robert Crow, has got some great videos where he goes fully in depth on TFX itself, which is TensorFlow Extended. We'll be talking a little bit around the TensorFlow libraries, which libraries have been externalized from within Google into the open source, how those libraries go to build components that come up together to be composed into pipelines of production. We'll also talk about the orchestration of those pipelines with TFX. And then following that, we're going to show how you can use Google Cloud Dataflow Runner as one of the runners that's available with Apache Beam to run a TFX pipeline. And at the end, if we've got enough time, I'll cover the building of a simple, customized ExampleGen. ExampleGen is one of the components from TFX, which actually consumes data. So we'll show how that is being built. And that's part of some of the work I'm doing right now around time series with TensorFlow Extended. So with that, a little bit around TensorFlow Extended itself. So why does it even exist? As you'll know, there is much more to machine learning than building that amazing model. So that amazing model, which is core to the ML piece, needs to sit within a lot of other things to actually make it production. So we'll need to deal with data collection, with how to serve the model when it's done, data verification, monitoring. So there's a whole host of other things which have to surround that model to make it possible to actually put this into production and put it into your operational systems at your company. There is a lot of tales from the trenches around how difficult that can be. So models can sometimes never make it to production, or models that take 3 weeks to develop may take years to actually deploy to a fully production system. And myself, as I've been working with the data scientists and building my own pipelines, I can see why, right? If you wanted to build all of those things that we described earlier by yourself, it would take a long time, from checking that the data is okay, to how do you serve the right model, how do you do A/B testing. There's a lot of things that you could hand build, and why reinvent the wheel? So ideally, what we want is we want a machine learning development environment along with modern software development together to become our production systems. So we want modularity, we want scalability. So data size today is 100 meg or a gig, and suddenly an event happens that you're getting into terabytes. Especially for me as data, I don't want to rebuild my entire system every time data goes up an order of magnitude. What we want is something that scales easily, is extensible, easily configurable, and comes with built-in tools for doing things like monitoring and testing. And this is the reason why TensorFlow Extended is so successful within Google. It's been running in production for many years at Google across many of Alphabet's important bets. And it is the key framework that's used when we're putting new things into production. So the things that have been built across all of these products, across all the time, all the battle hardening, all of that knowledge has gone into the libraries that have been pushed out and are open source along with TensorFlow Extended. And what that allows us to do is turn this collection of things that need to happen. We want these collection of things to become our ML pipeline. So we want libraries that will allow us to help us with data ingestion. After data ingestion, the ability to analyze and validate the data that's come in, making sure things are shaped and look how we expect them to look. The data hasn't changed. There's no new categorical values that we weren't expecting. After that, we wanted to go through the feature engineering. So this is where the data scientists are able to extract interesting things for the model to learn from. And then going into the training itself, once we train and build the model, we want to somehow evaluate that model. We want to check that it's good before we quick drop it into our production systems. And beyond that, the infrastructure of actually serving that model and that being able to do inference across it. So these are the areas that TensorFlow Extended covers, and the various components that we'll run through will make use of these, will allow us to build a machine learning pipeline. For this talk, we're going to concentrate on those components which are actually powered by Apache Beam. So I find this is super interesting as someone who's been with Beam for quite a while. Here we're having a framework that's built on top of our framework, right, which is really, really cool. The specific bits that we're going to concentrate on are going to be around the data ingestion and validation, as well as the transformation of that data. So these are the components in TFX, and as ExampleGen, StatisticsGen, Transform. We also have SchemaGen, which infers the schema of the data, example validator, validating the examples that are coming in. On the other side, we have powered by Beam, again, the evaluator for the models. So these are the pieces that we will look at, and in the context of Apache Beam. And I'm quite happy that we've got this brand new mascot that was, I think this is the first time I've got to use it in a slide deck, which is super cool. He's looking very, very happy there. And the why TFX makes use of Apache Beam to do the processing of the data. Well, first of all, as we mentioned, TensorFlow Extended is what's internally used inside Google, and internally it actually makes use of Flume. So Flume Java was the paper that you may be aware of that came out quite a few years ago, and Flume Java is the precursor, the starter for Dataflow, and eventually Dataflow was donated to Apache Beam, and it became donated to Apache, sorry, and became Apache Beam. So the external version of Flume is Apache Beam, and therefore the external version of TensorFlow was naturally going to be highly predisposed to those using the same technology. Internally in Google, about 60% of the code base for Apache Beam's runner Dataflow is the same as the Flume runner that we run internally. And there's plans to converge that over to 100% eventually. So it made natural sense for TFX to make use of this, but when TFX were evaluating the framework they want to use, there were some other benefits that they considered key for their decision. So with Apache Beam, it's a unified programming language for both batch and stream processing. Today, TFX is only batch, but obviously we'll see what happens in the future with other pieces. Portability is super important. So the ability to run the execution engine of your choice, I think that's a key aspect, as well as you expect, extensibility. So the ability to build new input-output connectors and new transforms and output them as libraries for others to be able to consume. I mean, the Apache Beam vision is great for me. It's the idea, ideally, we want any developer to be able to program in the language of their choice, to be able to build pipelines in their language of their choice, and for those pipelines to be able to be run on their execution engine of their choice. So, for example, we have Java, Python, SQL, and Go in Beam, and we have runners like Google Cloud Dataflow, Apache Flink, Spark, Samza. So this choice is important, and it allows for TFX, for example, here, TFX's components, which are written in Python, obviously the data science language of choice. I write most of my stuff in Java, and I'm getting better at Python, but still a long way to go. And the language is Python. However, we want the TFX pipeline to be able to be run on any of the runners that the developer wants to choose. So whether that's in the Cloud Dataflow or Apache Flink, that's entirely up to the choice of the end user. The other benefits of going with the Apache Beam model for TFX is it just automatically inherits cool stuff from the framework, as you would expect. So one of those, for example, Apache Beam does liquid sharding. So what it can do is it can rebalance in a batch pipeline. You can rebalance the work that is on the pipeline with workers that have ended up with too much work. As long as they have keys that are splittable, as long as there's more keys, they can move those keys around and redistribute the work. So TFX automatically gets the benefit of this for any runners that support dynamic rebalancing, which is supported by the Beam model. Another advantage is obviously future work that TFX will automatically be able to make use of. So coming soon, I'm super interested and excited in this piece is cross-language transforms. So the ability to build a pipeline in one language and to be able to use transforms from another language within that pipeline. So if you imagine, for me especially, like I write stuff in Java, but there's a cool library in Python that I want to make use of, just being able to use it directly in my Java pipeline without having to do an external service call to another service that I've built that is able to execute that code. So this is coming, and it's super interesting, not only in being able to allow us to get access to really interesting graphs with different libraries and different languages, but also it will allow you to obviously make use of things that have been built for any of the other SDKs within the SDK of your choice. So Java was the first language Apache Beam supported, and it's more mature. It's got more utilities and functions. And with this ability coming soon, in Python, you'll be able to go and make use of those libraries and functions from Java directly in Python without someone having to report and rebuild that component for Python. The IOs are probably the most important one of these that would be really interesting for cross-language transforms, because the number of IOs for Java right now is a lot more than Python. And we have a lot of connectors to a lot of different to file system messaging databases. So having all of this available for TensorFlow extension obviously makes a lot of sense, because one of the key things we're going to want to do in our pipeline is that data ingestion piece. So excited to see all these things coming, and this is a very important reason why TFX went with Beam and is able to make use of all the good stuff coming from the framework. So now a little bit onto actually how TFX makes use of Apache Beam. And one of the interesting things for me, so there's a lot of TFX that's kind of like, I don't get, right? Around the model building itself and the data science parts. There's stuff in there that's pretty opaque to me. But the fun thing was, as I was starting to learn it, when I looked into the code for the pieces that use Beam, underneath the covers, there's actually just pure Beam pipelines. And therefore, it's very easy for me to understand what it's doing. And also later on, as we see, to try and customize something if we need to, it's actually very, very intuitive for someone who's building, who's comfortable with Apache Beam pipelines. So a little bit, just in case there's folks in the audience who may not be that familiar with Beam. With Beam, there are 3 core primitives that we work with: PCollection, power collection of unordered set of data for input and output, and pre-transformations, which work against one of many PCollections. So with this, we're going to transform the data within the PCollection and generating other PCollections. And then we have the pipeline object itself. So this allows us to compose compose various PCollection transforms together to build the end-to-end solution that we want. And the one at the bottom is actually a very common one. So reading from a database, doing some transformation, doing some enrichment, some shaping of the data, generating more PCollections along the way until we eventually get to a sink, which is the database table. So with these primitives, we can build interesting pipelines for the business. So in this example, we are reading data from our online stores and our bricks and mortar stores. So we're reading information that's available from the stores. We are extracting the item ID. So this is sales information that we're reading. And the item IDs for the online stores and the bricks and mortar stores, we're flattening those two together with the beam.flatten operation. We are then counting per key. So we're actually going to do how much of each item has been bought. And then we're going to do a top 10 of those items. And at the end of that, we're going to record those results in BigQuery. So on the right, we see a simple pipeline that's being able to do our analytics against the data set that we have. The built-in connectors make all of this fairly straightforward and trivial to build. And it's these same connectors and same components that allow the TFX libraries to do what they need to do. So here, and this is a sample from the TFX website, where we are reading, again, data from a CSV file, and it's text.io read from text. We are parsing that information, but then we are using one of the libraries from the TFT Beam, which is Analyze and Transform Dataset. Now that Analyze and Transform Dataset is actually got inside it a lot of the business logic that's needed and that I no longer need to write. So using that library, I can get all the goodness of all the stuff that the library has been built on within Google from the TFX engineers who have had lots of pain and corner cases covered over time on when they've been building these libraries. So all of that goodness is within that transform. And all I need to do is access it within my pipeline to make use of that. And in this example, I've actually expanded on this right. What we're seeing in this graph is I've expanded the Analyze and Transform Analyze and Transform dataset transform. Sorry, that's a mouthful to say, but I've expanded that. And inside it, you can see how many pieces of work and transformations are happening within that one action. So that one line of code generates a input, and we have input going into that and output coming out. But what it's going through is a lot of business logic that I no longer need to write. So that library is giving me a nice abstraction layer for that piece of work. And those libraries together are what go to build the TFX components. So as well as the libraries, we now have components that are actually building our pipeline. And those components, when stringed together, become our machine learning end-to-end pipeline. And of course, as we said, you can run these on different runners. Flink, Spark data, for example. So let's walk through a simple example of this. And for this, we're going to make use of the ever-present taxi data, which is available in BigQuery as a public data set. So Google Cloud BigQuery Data Warehouse in the cloud. We can actually use that data to actually test some of this out. Now, the components that we're going to work with, again, being a data engineer, it's the ones I'm most interested in. It's this beginning part of the process. It's going to be ExampleGen, which is going to be used for the data ingestion, and StatisticsGen, which is going to be used to analyze the data, to gather interesting statistics from that information, ready for the rest of the pipeline. So ExampleGen takes inputs of various formats. These are 3 different types of ExampleGen that are available: CSV ExampleGen, ExampleGen, and import ExampleGen. CSV obviously reads from CSV files. Import ExampleGen reads tf.examples stored in a TF record IO. So the one we're going to use is actually BigQueryExampleGen. So this is an ExampleGen component that's already been plugged in. Once we give it a query, it's going to be able to pull information from our data warehouse ready for the next stage. It's also, ExampleGen can also do the split of the record, so eval and training split, and does things like shuffling, etc., of the data. The next one will be StatisticsGen, and with StatisticsGen, there's very little to configure. As you can see, all we need to do is pass it the output of ExampleGen, and once it's in the pipeline, it will go and do the processing to analyze the data, as well as the outputs, which are schema and various information around types of data, etc. There's also some visualizations that are available that you can actually look at, and your data scientists can look into. So, sorry to show you code, depending on where you are in the world. For me, it's late in the evening, but what we're going to do here is just in terms of the data source itself. So this is abbreviated, but by the way, there is a blog post on the TFX blog which has all these code snippets. So if you wanted to go and try it out, just look up TFX blog and Dataflow, and you should be able to see this come up. But essentially, first thing we need to do is extract the data. For that, we're going to just run a query. And a couple of things to note from this query. First of all, you notice that we're actually doing a little bit of feature extraction here by doing extract month, hour, and day of week from the timestamp. So one of the interesting things I found with TFX that you can actually, there are different areas that you can actually start extracting and manipulating the data. One of them will be at the very start when you're reading it here, where we're letting BigQuery do some of the extraction for us. And the other thing to note, while we're in development, we're actually limiting the results to just 100. So let's imagine we're actually building this as a dev environment. We're playing around. We have a limit of 100, and this will result in 100 records being read from BigQuery. The next step is actually creation of the TFX pipeline. So the first part is some boilerplate that we require around arguments that we're going to pass in to the pipeline object. But the next 2 pieces are pretty straightforward. What we have is BigQueryExampleGen that's being instantiated along with the query that we had from before, and some output config. And then we have StatisticsGen. And again, StatisticsGen, the primary thing that we're passing into that is the ExampleGen's output value. So the location of those examples are being sent to StatisticsGen. And the pipeline itself, the array that we have here, ExampleGen, StatisticsGen, this is all we need to do to define the pipeline. And then TFX will go and run these components. Obviously, for a full ML pipeline, you'd have many more components in that array. The next step is to actually run the pipeline. Now, for the first run, we're going to use the direct runner, which is a development runner that is available with Apache Beam. It's where you can do your development work, run it on your local laptop, etc. The information that we need to pass is pretty straightforward. We just need to give our pipeline a name, the root location of the pipeline where the information is going to be stored, Here, I'm just going to send it to a local route somewhere on my laptop. The query, and even though this is a local run, we do need the Google Cloud project because we're going to be reading from BigQuery. So it needs to go off to the cloud and pull that information down, those 100 rows down. So it does need the Google Cloud project. Finally, we will come back to this Beam DAG runner and what that's doing a little later on. So with this information, we can go off. It will actually run on your local environment using direct runner. It will go through ExampleGen, which reads the information, and produce a StatisticsGen for outputting the information. Now, what would happen if we wanted to make that production? So rather than 100 rows of data, now I want to run it on everything which is in that table, which is around 195 million rows. Well, first thing we need to do, we just remove the limit. So there's no longer a limit on the amount of data being stored, just brought back, so bring back everything. The next thing, and this is where using the framework comes into its own, there's nothing else we need to change on the code side other than rather than running with the direct runner, we now want to run with the Dataflow Runner. And we do have to send in this setup.py, which tells it which version of TFX to use. Again, all of this is on that blog post. But with this, we can now run this on the cloud. And what that will actually do is, first thing, and I'm going to use the Dataflow Runner as an example, but of course it could be Flink, etc. The first thing that it does is going to start a batch up with BigQueryExampleGen. So that's going to spin up a pipeline and do the work of reading that data, doing the splits, the eval and train. And once complete, the Beam DAG runner will then start up the SchemaGen pipeline. And again, once that's complete, then Beam DAG runner will have completed its work and it's finished. What that looks like, and I'll actually show quickly show this on the console in a minute, what that actually looks like. So this is an example of the Dataflow monitoring UI, and we can see BigQueryExampleGen processing the data. It's going to do the split of the values. So here we're seeing branching within Beam, and that's pretty easy to do. You essentially just apply two different things to the data. In this case, some data is being sent to train, some data is being sent to eval. And the results of that are going to end up on Google Cloud Storage as sort of an object store as zipped files ready for the next stage. In terms of StatisticsGen, we will have two sets of data to work on. So you'll notice this graph has got two lines. One, we're reading the eval data, and one is reading the train data. I've also expanded some of the transform, the generate statistics transform, just to show that actually it's actually quite complex what it's doing and doing quite a lot of work. Or again, making use of all the libraries that are available via TFX to do the work. So I, as data engineer, don't have to rebuild and reinvent the wheel. And the output of that, we will be able to visualize, of course, with the graphs, but it also producing artifacts that are going to be used in the other parts of the pipeline. So just quickly going over to a demo. Well, more of a show of the monitoring UI rather than a full-blown demo. But this is a job that I ran with all of the rows of data on Dataflow. So this is the monitoring user interface. And we can see the DAG, again, with the split data. If I was to expand this transform, so clicking on that top arrow, and hopefully my bandwidth is good enough that you guys are seeing all this. We can see that we're querying the table. We are converting over to TF examples and doing the splits, etc. If I was to, let me collapse this now and select it. So here on the right-hand side, we see that it read 193 million rows of data. It's about 100 gigabytes. We're seeing some throughput graphs on what it was doing. A new feature that was added to the UI, if I go to job metrics, we can actually see some of the stuff that's been going on in the background while that pipeline was running. So this is the autoscaler of bringing in more cores to bear. The green line is what it was suggesting. The blue line is what I was allowing it to do. We can go down and actually look at some of the throughput. So elements per second. These graphs are super useful when we're debugging, especially performance bottlenecks. because what we can see at the bottom here is the fused steps. Beam will fuse steps that don't have a aggregation, basically essentially a shuffle within them together for efficiency. So we can see the fuse steps here. And if I was actually to select on this graph and roll back time a little bit to something where there was some more activity happening and select the values, I can see the throughput rates at different values for those different fuse states. And again, with CPU utilization as well, we can see what all the different cores are doing. This is really good graph for trying to find things like what is where a bottleneck is happening, especially this one here. And of course, if you're more interested in the bytes process rather than the elements, bytes are available as well. Now going back, I'm going to change to the next job. So this was the ExampleGen job that was reading the data. The next job is the StatisticsGen. As we said, there's two flows. One is reading the train data, one reading the eval. Actually, my apologies. If I just go back, just to look at the bottom of the values. Sorry, I'm all fat thumbs at the moment. Wrong one, sorry. There we go. So just going back, this is the ExampleGen. Sorry for the confusion there. Go back to this one. Just want to select, if I select the train, we've got 145 million rows being sent to train. Eval's got 48 million rows being sent to it. Now, if we go back to the next, so we go to the next stage, which is StatisticsGen. If I select on eval, we can see this is the 48 million rows. So in that step earlier, when we were defining the graph, we passed on the output of ExampleGen to the input of StatisticsGen, telling it where the files are. So it's used that to actually find the files, process them, and the training, of course, 145 million. Again, there's probably a little bit more interesting stuff going on in these graphs because there is more going on in the StatisticsGen rather than just reading. Again, we can see, what's that about? 1 megasecond being processed there in terms of elements. Another interesting thing with Beam, you can define counters. So the TFX team have got lots of counters that are being put in for these features. And we can see if I go to, for example, the number of integer feature values that it would process, it was over 1 billion. Okay, so moving back to the screen, and I'm going to share my screen. Just before I do that, is everyone getting the updates and stuff okay? Is my internet working okay? My voice is okay?
Yes, so the chat is disabled, so no one can actually reply now.
Ah, okay, great. So as we noticed in those steps, there was 2 distinct pipelines being run. The first one was the ExampleGen. The second one was the StatisticsGen. What we're actually doing is we're actually creating that. To create that pipeline, we need to orchestrate all of those components running in different places, and TFX orchestration layer does that for us. Let's have a little look about what that means. So we have ExampleGen, which is reading that. When complete, then we spin up StatisticsGen, which takes the data. StatisticsGen would eventually go to SchemaGen, which can do the inference on figuring out what the schema looks like for the objects. The outputs of these two can go to Example Validator. All of the SchemaGen and the ExampleGen go into our transform component. So if we look at all this, as we build out this pipeline, it's actually looking like a DAG, so a directly executed graph. So essentially what we've got now is a series of components, which themselves are DAGs, and a larger DAG, which is the pipeline itself. So we need something to run the DAG of DAGs. That's a very lame joke by me about let's go deeper, referring to a certain film. What would the orchestration layer need to look like? Well, if all we needed to do was fire up the next stage of the pipeline after the first one completed, we just needed a task-aware pipeline. However, TFX needs much more than that, and does much more than that, because you have the ability to rerun various stages. It stores metadata about the runs and the information about the pipeline as this is all happening. And this is task and data aware pipelines. So it's quite sophisticated. I won't go into huge detail around the metadata. Again, if you want like really deep on TFX, Robert Crows does a great couple of sessions where we go in depth on all of these components. But in terms of what we can use to do the orchestration, so as I understand the Meetup, I had an Airflow session yesterday, was it, or last week? So you can use Airflow, you can use Kubeflow, and also, because essentially what we're doing is building a DAG, and Beam can be used to build DAGs, you can actually, that Beam DAG runner, that Beam DAG runner operator that I was referring to earlier, it can be used as well. So in development environments, etc., we don't need to bring the other stuff in. We can just use that to orchestrate our pipelines. How am I doing for time? Okay, I think we've got a little bit more. So I will go to the next bit, which is around the building of a custom component. So one of the things I found useful with TFX, because it's using Beam underneath, and if you're familiar with Beam, building out some of these custom bits actually is quite straightforward. Why would you want to build one? Well, one interesting thing is, remember when we get those cross-language support with all these different IOs, it may be that you want to build your own custom ExampleGen, which digests data from multiple sources. You may even want to build your own IO. And that's one of the things that I've tried to do with one of the work I'm doing around time series. So is to build a ExampleGen which is specific to my problem set. And actually doing that is pretty straightforward. So what do we need to do a custom ExampleGen? So ExampleGen being one of the components of TFX, there are 3 out-of-the-box ExampleGens available. There's CSV, there's BigQuery, and the import that we talked about earlier. If you look at the source code for these things, the underneath is, sorry, just bear with me. Yeah, underneath we're like reading from text, io.read BigQuery source, io.read from TF record, and apologies, I've got StatisticsGen there, that's incorrect. That should be CSV ExampleGen. I should have a checker, code checker for a slide. Sorry about that. That StatisticsGen equals is wrong. That should be ExampleGen. But anyway, in the source code, we're just using Beam language to read the files. And therefore, if you wanted to build your own one, first of all, apologies, there's boilerplate. So first thing we need to do is build a PTransform that actually can read the data. And there is some boilerplate on the signature for the transform that you need to create, which is most of this lines. The interesting part is at the bottom, this is the thing that we need to do to build this ExampleGen. So ExampleGen's output is a tf.example proto. That tf.example proto is what we need to produce. And in order to do that, we can use simple Beam primitives. For example, read my custom data. I've got beam.io, insert your IO of choice here. So this would be something that you would do to read data, or it could be many sources of data that you're flattening together. And then you parse that data into a tf.example. As long as you do that, you've essentially built most of everything you need for a custom ExampleGen. The next couple of little bits of boilerplate that need to be taken care of, we'll need to create an executor. So that code that you wrote for writing the example, you provide it as a return object to the executor. And from there, we now create our own time series ExampleGen with this custom executor. So with that, we will be able to run a TFX pipeline. And in this example of mine, I'm actually doing a couple of things. There's some special metadata coming from another part of my system that I want ExampleGen to understand, as well as some TF example records that I'm landing. So what I do is I use a side input to the Beam pipeline to actually bring this stuff together under ExampleGen. And with that, I can put it into a standard TFX pipeline and treat it as normal. A couple of tips around this. The custom ExampleGen My data scientist works a lot in Jupyter Notebooks. I tend to work in my IDE. It's just where I'm comfortable. But there's a couple of things that he pointed out that was super helpful to me when I was building and experimenting with my ExampleGen. If we put into a notebook interactive context, and we can then run these components individually without having to build the whole pipeline. And more interestingly, we can access the output of each one of those components and visualize them and get to play with them. So for example, here, my time series ExampleGen, I can run it from the interactive context and I can print outputs from it. But much more importantly, as data engineers, it's usually data we're trying to look at. So here, what we can do is use the dataset API from Tensorflow, and we can parse the data that's coming out from that previous step and output it to the screen. So just to quickly show what that looks like, I have a pipeline here. I built this executor. I have my code for the reading the data and the metadata. The next step, I create the interactive context. I run my time series ExampleGen. We can see the outputs that are generated from that. We can look at the variables, and more importantly, we can actually look at the data inside. So here we can see some sequence lists of timestamps as well as other features. And I found this super useful as a way of like debugging and working with my terrible code. Moving on from there. Okay, so up to now, we've gone through a little bit around TFX. We covered a little bit how TFX makes use of Beam, gone through a couple of components, how you can run a Dataflow Runner with it, how we could build a potentially a custom ExampleGen. Another, just a piece to finish it off with, the work I'm doing is as you'd expect with Apache Beam, a lot of the coolness comes from our streaming pipelines, and the data I'm working dataset I'm working with time series. So the architecture that I'm putting together for this is to use Dataflow to do the stream processing and also some feature extraction. As we mentioned earlier, there are different places that you can do that. I land TF examples into our object store. These TF examples are sequence examples for the time series. And then we pull off TFX pipeline against that Google Cloud Storage. That line you see from Dataflow to Tensorflow is the signal that something's changed enough that we want to run another pipeline. With that, again, I'm sure some of you would really like to get deep into TFX itself. On the Tensorflow site, we have Robert's videos are fantastic. He really goes to a lot of great detail and makes it very easy to understand. So I'd recommend you looking at those. And obviously for Beam itself, or the Beam website and experimenting there. And with that, thank you very much for listening.
So I'm Alex. So I'm an Apache Beam committer. So I'm the person that worked on the schema where PCollections. Certainly from my drive to have better protobuf support that has like a very rich schema system, and I wanted to have it like full scope. So this feature was needed. So that's something I do in my nighttime. In my day job, I'm a principal engineer in Colibra, so it's actually a nice combination. It's all about data integration and the feature, also schema. It's about schema, so it's a very nice combination, and we're now building the newest cloud-native platform for managing all your metadata. So I want to actually start with this quote from me from yesterday. I actually invented that one yesterday. So developers, they're actually so used to working with annotation in Java or .NET or decorators in Java or whatever it's called in other languages. They're so used to having their data types, putting annotations on there, and actually expect like a behavior change in the code. But if you're working with contracts, be it like Avro contracts, JSON schema, or protobuf contracts, people are not so used to that. And having this new schema-aware options in there, it actually hopefully will bring that more to the mainstream. For people that are not aware with schema-aware PCollections, and mainly still code with your native objects in the code. Schema-aware PCollections actually augments your elements, be it like a Bojo in Java or like an Avro class or something. It actually adds the schema information on top of that. So for this to work, people have written like schema converter of schema registries to make make your element that's in your pipeline actually more intelligent, or not more intelligent, but have more context. And that's done by actually adding a schema to your schema that is actually quite universally understood by the Beam pipeline to your element. So be your element, it could be like a plain Java object. There are converters for it to actually augment that and create a schema on that. So if you have like a class with 2 integers and a string, that converter will make like a row class that actually says, oh, it's an int and a string. And from there on, your pipeline is actually aware of the schema. Those schema providers actually also create like a way to convert your element automatically to a row and back again. For me, the interesting part more for in the discussion along in the slides is more towards the to-row function, because those to-row functions only will be triggered or transform your element to a row. The row is actually something that Beam understands along the way, only when needed. So those conversions will not be done when it's not needed. So for example, if you have like a job object, and you can use the universal where a field name of one of your elements, when your fields of your object is with that name is between that value. That's quite universal, and that with name is not and it actually doesn't care what type of element it is. It could be like a Bojo, Avro, Proto, whatever. This one line can be written for all of them. It's not that you directly access, have to write code, statically typed code to access that. This brings those functionality to your pipeline. But if there is like so that means that actually your element stays intact unless you make like a destructive operation. For example, if you have your element and you only need like 3 fields for it, of course it doesn't retain your element anymore. It just creates a row with storage, with its own storage, and from there on, further in your pipeline, it gets like a reduced element with all of those things. So, but those things are only done when needed. So those are the built-in transformation that you already can do on your row. So as soon as you have like a schema provider for your specific data type, be it element, proto, whatever, you have access to those transformation functions out of the box. But this is standard schema PCollections. What I'm more interested in, though, is that that actually the metadata that you can build on top of this. So it's kind of strange that you even have need for like another layer of metadata, because schema-aware PCollections, the schema, the row schema, is already metadata that augments your element. Sometimes it's even actually more even interesting to have like extra metadata. Just like those annotations that developers are so used to. It's actually your class has like a type that sometimes you want to add something to it. And that's the metadata. It's actually from the beginning, it was already available, but it was quite very basic. It was only available on the type. So it was just key value pairs. And those key value pairs, well, it was a key that was a string, and in the value, it was just a binary field. So you could do a lot of things already there. But it was only available on the type, and you actually lost like a lot of lots of type information. Although you could do some tricks with it. But as I was working on the better protobuf schema-aware PCollections, protobuf has like a lot of extra more type information, and I just wanted to get that in. But I'll give you a few more examples later. So sorry. So this is what you already could do like that. Sorry. So up comes the improved improved options or metadata. So the first thing is like introduce like strict typing. So instead of like just having a binary value stored on top of your type, so if you have like a Boolean that you want to store, it's far more easier to use those types than having like doing first a conversion from your binary field to a Boolean and then do an if then else statement. I have like an example. Well, I had an example here. So yeah, that's what you get. So if you have like in the past, it's a binary. You have to do some things like there or do other type conversions. So here here I parsed an integer. So you have to write really a lot of boilerplate to access that integer. You have to parse it, first get it into a string. Is it an empty string? Because it always returned empty, and then parse it, and then you have your key. While with the new functionality, you just can get like on the fourth line here, your integer, you just get the value. If the field options in the beginning was just an integer, you get your integer back. And those get again out of the box. But yeah, why stop with primitives? While you're working on a type system anyway, why not support everything that Beam already supports? So we went all the way and also supports like getting map information in there, arrays in there, and even the rows as well. So here we don't, if you set options, you don't need to specify which type it is. So this is the setter. You have the getters in reverse, of course, because the row itself contains a schema, so you don't have to specify the schema anymore. But the classic metadata was only available for on the type. We actually removed it from the type and moved it to the field and the rows. So if you look at the left, that was before where you only had the binary metadata. Now we have like the typed information on the columns and the rows itself. So it's kind of, you would think, why do you need it? It actually pretty convenient if you have like those options available, because rows in itself, row doesn't have like a name in Beam. If you kind of used to like other systems, like for example just the Java type system or protobuf, in general a row or or the containing type has a name. But as Beam is more like a row based, a row in general it doesn't have a name. But if you want to retain this name when you come from another type system, for example, and that's what I actually learned while implementing the protobuf implementation, is that you actually want to retain those original names. So this is a protobuf message where you have like the well-known type message that's actually the type of the message. If you want to convert that into a Beam row, you actually want to have that name in there. So, and because you can store it there on the row object, that's where it should be. It should not be like on the type of the field. No, it should be in the row. So while implementing that, we started using conventions for like, if it is a proto-specific metadata, we're just starting to put that on a URN name type prefix, where you have like Beam option proto, because then it's like the proto metadata and the type name that's been added with a buff value. Proto has like for each field like a number integer, and of course we can also add that to the metadata. So if you need that access to those proto-specific features, you have access to it. And all those metadata that is available in protobuf, we are now storing them with specific prefixes. I'm talking a lot about protobuf because that's the first implementation that has those schema options. There is one ready for Avro as well, but that needs to be approved. It's in a pull request. It just uses, it's very similar. Less typed though, although we can get some types like pure integers and strings, we can detect that because like Avro uses JSON just as its schema carrier, and it's not that type safe, but it's pretty well supported for some types. So those will be then prefixed by Beam option Avro and the specific thing that's in there. Voila. So that's then pure theory, but then what can you do with it? And that's probably more interesting because it actually brings like a change in mindset when you build a pipeline. Of course, not all pipelines should be built dynamically, but more if you have like metadata on your like contracts or schemas, you can actually put annotations in there and actually drive your transformation. And that's what I'm going to show. So in general, we're talking here like doing very similar transformations. At the end of the presentation, I will go through an end-to-end solution where we do like encryption of certain fields for personal identifiable information. But if you have like tons of like contracts, like maybe 100 of contracts that come from a system, and you want to write for each and every one of those messages transformation, what do? You create an event where you change X into X changed. So you do a transformation specific for that. But so if you have, that's when you have 1. If you have 2 and 3, you have to write very similar do events. And after a while, it gets like messy. So certainly if you like 30, 40, 100 do events for like doing specific transformations, you have to test them all and all and all. But if you have like those metadata on your contracts, on your in your schema, you can actually change instead of writing a do-event, having like a transform that does that for you. In the beginning, when I started using like Beam, I only actually thought of the transforms as a very nice way of like grouping your do events. And that's kind of nice if you run a data flow, then you have like your box, you can collapse it open and so on. So it was a nice way to organize it. But actually transform are very, very powerful because they execute at this construction time of your graph. And you can do like a lot. So you have actually more access to your input and output schemas, and well, your input schemas and metadata of what's going to come at the construction time. Then you have your new do event. So what I want to show you is actually that you can, from that schema, actually in an expand, you can expand your graph in there. But we'll go a little bit into detail. But you write it once in your expand. So in your expand, you actually create your to-do events within that graph. But you can just reuse it if it's specific use case for like the example of the BII. You just create this. It's just one transform that you write, and you just execute it and just give it another schema, and it creates like a new branch again and again without writing any code. In your code for that transform will be bigger than one do event for a specific use case, but if you have to do it 3 times, you will gain like having a transform. So some examples of what we could do with it, and what I did in the past is like we were kind of contract first, very contract first, and the data that comes from a system, we actually annotated, for example, where you have a contract for a shopping cart. So the contract was made, but sometimes you have like composite keys where like a uniqueness of an entity is defined by multiple fields. And instead of like sending that extra and letting the source system define the unique key, you could make Beam actually, by adding those annotations in your contract, say, okay, this and this makes this object unique. And you can make Beam actually create that composite key into a single object. Like, for example, having a string that concatenates all the values. And that one can then be stored like in BigQuery, or maybe you want to do some reversal or hashing of that key as well. In that case, if you store it like in something like Bigtable, where it could be handy to have like different kind of access keys. So this is how you would then define it in protobuf, and in Beam, in your transform, you look for those example key annotations and then do your stuff, and then make a new row out of it, and then give it back to the next transform. Something else is like collapsing objects. So remember, most of the things that we're talking about is like hierarchical. It's like, yeah, a lot of people like to work flat, but I actually like to work hierarchical, where you have like address could be a part of a user, and an address is a separate kind of object. But sometimes you actually, that's interesting to communicate with business. But sometimes you really want to collapse them if you store them in BigQuery, because then it makes it a bit easier to query, certainly if you want to have like some top level things defined. So you could do that in the same way. this is an example where you actually want some fields, but every field is like has metadata, but that metadata you want to always like collapse into your target system. And then you make like a new row out of it. And instead of like copying it everything over in a new object, you create one transform that does that for you. If transformations will be too complex to create in code, then actually you can now Beam has like a nifty new feature. Well, it's not so new anymore, but the Beam SQL are working on those row objects, and you can actually read your those annotations, those options, the schema options, and create like transforms. Like an example here is you can say, okay, we have like field 3, it's a date time, but we only are interested further on the pipeline in the day. Then we can actually add those two annotations, and it will create like a select graph that makes like the transformation for you. Other use cases are data quality checks. So the system you don't have that's transmitting data to you, you don't have like control over it, but you want to do like data validation and report back to the producer of the data if that data is like within the expected range that they told you. You could actually validate that while with putting like annotations on there in the same way as I showed you already. Something I was considering is like there is like a nice, again, the examples that I show is like very proto-buff specific, but it's not, those principles are applicable to everything. Is like in Envoy, they have like a nice validation library. It's a library, but it's like the proto options that you can put there. And just by using them, they are available in Beam. And if somebody would write like a transformation that recognize those options, only one person has to write that transformation. That's for if it's okay, then it goes through. If it doesn't validate, it goes to the dead letter. Could be a second round. So another use case is adding semantic meaning. So beyond logical type, a good use case there is like Debezium. I don't know if people know Debezium, but it's like a famous Kafka connection. It's not written. It's like actually a change log data capture. So you connect it to your database. It does read those things and actually produces change string. It has Kafka support, but you can employ it in other systems as well. I have like an implementation that wrote to protobuf, but it also has like a lot of primitives that you construct. But in those databases, there are sometimes very weird data types that are supported, and certainly like the different kind of date time formats that they have. So instead of like pushing everything in the Bayesian, what they just do there is, okay, we'll just put or an integer or a string and let the downstream system handle it. We just put information on that. And this is actually an example that we're really using there, is that in Beam, we can just say, okay, it's a string, but if it has the annotation put by the Bayesian on there, like it's a zone timestamp, okay, we change we're not going to handle it as a string anymore. We're going to change it as a date time. Of course, you also have like the thing that converts not only in the schema, but also the value itself. A few examples. One is string, one is an integer. It has another kind of timestamp, semantical type. bytes, for example. If it was originally a Java decimal, it is just put there as a byte. It's up to you to actually decode that. And we've written some code in Beam that actually then transforms it to the decimal type that we want. So putting it all together, the GDPR use case that I already quickly told you. So what were the requirements there? We wanted to encrypt the personal identifiable information. We wanted to have, like, for each user a unique key, so we can do forget actually the original user just by actually destroying the original decryption key. So that's the right to forget. Because deleting a user is not very not so straightforward if you have like a very big company where the user is distributed in lots and lots of systems. So the goal was then actually just to delete the key, so we don't have like any notion anymore of the user was. And sometimes you need to keep some data of a certain customer, like orders and accountancy stuff. So the building blocks in this user case, so the schema options, of course, the new schema options. The target system was BigQuery. We want to get everything in BigQuery, and it has like a nice encryption library. And Google was so nice to have like a Java counterpart available that we could like use in Beam. It doesn't have like Beam functionality itself, but it's Java, so we could use it there. It is Google Think. It is the same encryption as BigQuery. Of course, we needed somewhere to store like our keys, and that is then, of course, again accessible by BigQuery. So we store them in BigQuery, and made it available to BigQuery. So store it in Bigtable and make it available in BigQuery by federation. So you can have like a view on a Bigtable table in BigQuery, and so you can join it. So this is how it would happen. So you get like you have your schema, and we used our schema from a schema registry. Could be whatever kind of schema registry. We get our schemas back from that registry, and then for each and every one of them, we just give that type to a transform. We create a new transform for each type we're interested in. Well, we write the code once, but at the runtime, we give the schema then, and in the expand function, there it looks like it will look, is that PII option field in the metadata? Yes, okay. Then we'll create an output schema because it has to be done upfront in the expand function, where actually the output, so if it's in the original field was a string, and the target is then a binary, because yeah, it's just binary scrambled data. That was the output. So that's where the schema change happens. And then it creates those do events. It's like as I showed, like where you have one transform with lots of building blocks shown. That's what's happening here in the expand function. So it's also stateful processing. So we needed to actually make a key value pair out of it, take the user ID, and then have the new constructed row. Because stateful processing always happens on a specific key. You cannot do it like in a global window, and it's kind of handy as because we used it as a caching function of our encryption key as well. So what happens then in the main building block, in the domain block there, we encrypt the key. Is an encryption key available for that user? If not, we create one and store it in Bigtable. So it's like a double arrow. So it first will look into Bigtable, because if the pipeline was stopped, there's no keys in the data stateful processing. So we will first look in Bigtable, is there one? Yes, okay, then we'll use that one. If there is not one, we will create one and we will push it. Because of the stateful processing, this will be all atomic, because everything is serialized per key. But there's still parallelism because it happens in parallel per key. So then we traverse through the complete row and encrypt the fields that have the PII option. And then we output the row. At the bottom, you see rest of pipeline. You can do like lots of other stuff, and then it ends in BigQuery. And then in BigQuery, you join it with Bigtable and decrypt it when needed. An expand can optimize, of course. So if you give it a schema, there is no PII option on any of the fields. It just puts the row. That's it. No need to create or traverse the complete graph of the row. This is a very naive implementation where we just go over the row, and that's a bit how it happens then in the code in your do-event. This could be even more optimized because this assumes that you already have like the row, and you always get the schema. But if you want to go really advanced, and I have to say I haven't done this yet because it's very tricky. But if it could be maybe worth it if it's very performance intensive. That you actually generate the code that traverses the graph, and then you can go much faster. But that's kind of a nice to have later. So what's still to do for schema-aware options? So Avro, so that's implemented. So just waiting. It will not make next release. All those things that I'm telling you here are available in the next release, and that will come out in a few weeks. But Avro didn't make it yet. Drift is actually very similar to Protobuf. It's also kind of new to be. If there are any takers for Drift from the meta support, I don't know there, but I would like to see actually everything supported for the schema options. Probably you can do something for JSON schema and XML schema as well. And actually making this presentation, I was thinking, hey, maybe we can do it like with the Pojos, where you have like an annotation there. Actually transform that annotation that you put there reflection-wise. You can also put that as a schema option in a schema. Certainly in the proposal is like this SQL extension where you actually write your schema and add options that you can then directly write. That's also available further on in your pipeline. So that still needs to be done. IO support. So for now, it's actually is only supported by Protobuf and then soon Avro. But iOS could also like add like a lot of more meta information, like GDBC, for example. GDBC has like a very rich metadata interface. It would be very useful for some transformation to have those available in your pipeline. So at startup time, it could like just query those metadata calls from GDBC and just populate the schema. And don't forget, it's only done once. It's not per element. It's available in portability, but only implemented in Java for now. So first schema where PCollection needs to move to Python and other kind of things, but in the communication between the languages, those schema-aware options are available. So as soon as work will be done on schema awareness in those languages, it will be automatically available.